used to live here. And my grandmother on my mother's side, also, well, she wasn't actually born here, but she lived from quite a young age in St. Petersburg. And I was trying to make sure I knew exactly where the house was in case I was interested in looking for it. And I knew it was in the street where the US consulate is. I only just learnt the other day from my niece that it is where is the now US consulate. That was the house that my great-grandfather used to live in. So I must go and have another look at the place. Okay, well, I want to say something, and I hope that people aren't too expert on my ideas, because a lot of things I want to say here will be things I've said many times before. So I apologize for that. I want to check that that does block it off. Yes, it does. Wonderful. Okay, that's fine. So the title here is Why New Physics is Needed to Understand the Conscious Mind. So I'm being quite definite here. I think that it is needed, and I'm just trying to explain why. That's the basis of the talk. Well, I don't know too much about consciousness. I don't think many people do, so that's probably not a disadvantage for me. But I do want to concentrate on one aspect of consciousness. Now, let me say, give a lot of points here that are relevant to consciousness. Well, you see, it has many manifestations. Some of them are passive, and some of them are active. You see, I think the philosophers call qualia, the things like redness and pain and things like that, which are conscious feelings and so on, or the active things, and free will is that. And I have a lot of words here. I won't even bother with them because, although they're terribly important, they're not what I'm going to talk about because I haven't got too much to say about them. But I want to concentrate on the word understanding, which I do regard as a manifestation of consciousness. So that if a computer or a computer-controlled robot were capable of understanding, it would have to have consciousness. That's the argument I'm trying to make here. And I'm using three words here, English words. I hope they're a good Russian equivalents. These words are words that I would hate to have to define. In fact, I wouldn't know how to define them. The word understanding I mentioned before, the word intelligence and the word awareness. And all I'm going to do as a mathematician, I'm allowed to talk about things that I don't understand, provided I can talk about connections between them and maybe something implies something else. So I would say that the word intelligence does require understanding. It seems to me it doesn't make too much sense to say of an entity that it is genuinely intelligent if it doesn't understand anything. So understanding seems to be something that to be intelligent one would need. Now, the word understanding, it seems to me also, although I don't know what either of these words really mean, understanding is something which does require awareness. I think it's unreasonable to say of something that it genuinely understands something if it's not even aware of it. I mean, the normal usage of the word, people talk about computers and say, does my computer understand this? They don't mean that. They mean understanding in a different sense. The sense I mean the word understanding is one which does imply that there is some awareness present, so that a genuinely understanding entity would have to be aware of it, of what it's trying to understand. So if understanding can be shown to be beyond computation, and that's the idea, then intelligence is not a matter of computation, and moreover certain aspects of awareness, and perhaps all of them, are beyond computation also. So I'm going to address the question of whether, I mean, this is a thing that sort of AI people who work in artificial intelligence, often say that, well, does their robot have consciousness or something? And they might argue it has or it hasn't. But it seems to me, or does it understand something? And if it understands something, I would claim, in the ordinary sense of the word, it really would have to have awareness. It's relevant, for example, if you want to build a robot and send this robot to a distant planet. People often say that, well, wouldn't it be wonderful, you don't have to send a human being out there. If you had a robot which really was very good with artificial intelligence, you send it to some distant planet, and the key thing there is you could just leave it there. You don't have to bring it back. It seems to me that if that robot actually did have awareness, you would have, if it was really conscious, you would have a responsibility to bring it back. So there doesn't seem to me I mean, you don't often hear people talk that way. You say, well, you'd have these robots visiting these distant planets. I mean, we're a long way from that anyway, but it seems to me an issue that would be relevant is whether that robot, if it really was intelligent, and if it really did have conscious things that you need consciousness for to behave, then it would not solve your problems about not sending humans, unless it happened to be very small and was therefore cheaper, I suppose. But those are issues that one has to think about. Okay, well, let me start by talking about something that we know computers are very good at, and that is playing chess. So we know with Deep Blue and all these things, computers can play wonderful chess. Well, we sort of know why, because they compute move after move after move and after move and so on. Now, there was, I think quite often there are these so-called Turing tests where they might have a lot of computers and people, and you have to try and distinguish one from the other. And one way would be to give these things a lot of chess problems. And there was, this was done by William Hartson and David Norwood several years ago, and they devised a whole lot of chess problems, half of which were easy for human beings and difficult for computers, and the other half were easy for computers and difficult for human beings. And this was a very nice example of a chess position where white has to play and draw, and it's pretty easy. You don't have to know much about chess. I'm not an expert in chess, and I can pretty well see how to do this one. Whereas if you give this to a computer, well, you see here we have almost a barrier of pawns, except there's a gap here. So what do you do? Well, white is to play, or the brown pieces, if you like, to play, and draw is the idea. And you notice that there is a great advantage in the black pieces. There's two extra rooks, and so this should be a hopeless position for white. But all you have to do is block, bring the bishop there, and then you have a completely impenetrable barrier, and the black pieces can't get across. And so there's no way you lose the game. Whereas if you give this to a chess computer, I don't know what the status is now, because this is quite an old problem now, and it's been, people know how to do these things and program them in ways that can work out things that they didn't originally have to do. But in those days, it would take the rook, you see. And taking the rook is very stupid because you have then a gap in the barrier, and the pieces can eventually pour. So it takes a while, so that maybe your computer wouldn't be able to calculate that far ahead. Well, the point about this is not so much whether the computers eventually can solve these things, but that it's easy to tell the people from the computers. It really was. So half the problems were easy for humans, half for computers, and it was easy to tell the computers from the humans. So that's just telling you that whatever the humans do is completely different from what the computers do. So that's really what one's trying to express here. Now, there is a problem with chess in that it is a finite game. And so that is, you could have, it's not the stage people are at yet, but you could imagine with a little bit more development of computers, they could completely work the game out from beginning to end. And so that it would be solved in any chess position whatsoever, the computer would know the right moves. Know is the wrong word, I shouldn't use that word. The computer would be able to make the right move and win if it was a position that was winnable. So in order to make the distinction a little bit more precise, I want to talk about things which are infinite. And this is the crucial thing. Chess is a finite game, and so, as I say, maybe will be completely solved by computers one day, but mathematics is often about the infinite. And how might computers be able to deal with the infinite? Well, with human understanding, we can often deal with infinite issues. I mean, we can't necessarily always deal with infinite issues, we can very often. And I'll give you a simple example of how we can deal with infinite things, and in a completely reliable way. It's one of the most elementary ways we do this, and it's learned in school, and one of the most basic procedures, which is what's called mathematical induction. And I'm talking now about the natural numbers, the numbers 0, 1, the non-negative whole numbers, 0, 1, 2, 3, 4, and that clearly is an infinite sequence of things. Oh, sorry, put it down there so you can see this. An infinite sequence of things. And if you want to prove a proposition, which depends on n. An example might be, is the number expressible as the sum of 4 square numbers? That's a famous theorem due to Lagrange, and it is summable. Every number is the sum of 4 square numbers. I don't quite know how you prove it directly this way, but this is the way you often prove things, generally for n. If you wish to prove that p of n is true for all natural numbers n, you could first of all establish that p of 0 is true, and then you show that if it's true for n, then it's true for n plus 1. So these are two things you can do. It's completely finite. You do this and you do this, and automatically you have all p's for all n's. So you could prove an infinite number of things by just doing a finite number of things. So this is very common in mathematical proofs. You have procedures which can be finite, can be checked in finite ways, and nevertheless can establish things to do with infinite numbers of things. This is what's called first order piano arithmetic if you include ordinary logic together with this principle, but let's not worry too much about that. But I want to raise the question here, are computational rules, such as those provided by ordinary mathematical induction here, sufficient for establishing the perceivable truths in arithmetic? And there is this famous result of Kurt Gödel, which says no. And I think I want to put this theorem in Gödel's in a particular way, which is the way I want to use it. People often phrase it in a different way, which I find more confusing, but let me say the way I mean. Again, we're talking about natural numbers again, and we might have propositions about natural numbers, such as every natural number is the sum of 4 square numbers, for example, or every even number above 2 is the sum of 2 prime numbers. The first one is been known for quite a long time, used Lagrange. The second one is still unknown. So we have examples. You can make some which are very easy. The Lagrange theorem is not so easy. The Goldbach conjecture, every even number above 2 is sum of 2 prime numbers, is so difficult that we don't yet know whether that's true for sure. But what does Gödel's theorem say? Well, let's suppose you have some point about these is that they are things that could be checked by a computer. I'm not asking that the computer should be able to find them, or that that's closely related. The key point is that can the computer check whether you have actually used these rules correctly, whatever they are. And suppose we have a set of rules R which enable you to prove propositions about natural numbers. Okay. And I want to say that let's suppose we trust R. Suppose we look at the construction of R and we say, yes, that seems all right, that's okay, yeah, okay. Everything that, if the computer program says yes, that is genuine proof. Suppose you trust R in that sense. Well, what does Gödel do? He produces a very specific statement, looks at R, and by a very specific, in fact, computational procedure, you can construct a statement, G of R, which, if we believe in the validity of R, if we do trust R, then we must trust G of R to be true. And you can see it's not that hard. I could have shown today, but the other things I want to say, it's easy enough that I could have given that demonstration here. It wouldn't be hard, really, at all. Very subtle, of course, but not hard. That if you trust R to give you only truths, then you must trust G of R also to be true. However, you can see, by the way you construct it, that it cannot be proved using R. So that the rules that we use to understand the truths of statements about natural numbers are not encodable in any R that you can construct and believe in. So there are possible loopholes to that, but not what I said. I mean, if you trust R and you know how to go through this, which are pretty straightforward, I mean, the question is really whether you trust R. It depends on R, of course. You might have some R's that you might be doubtful about. But if you really do believe that R does only give you truths, then you must also believe that G of R gives you a truth, and you must also believe that G of R is not obtainable by R. So how do we know G of R is true? Well, you just follow the argument. You can see, it's, as I say, I could have given it to you. Sometimes people say, well, these things are so incredibly complicated that why bother with them? Well, I'm going to show you that that is not a fair way of dealing with it. I gave you here the procedure of mathematical induction, and that gives you a perfectly well-defined R. Now, suppose you have that. Can you prove the following thing? Well, I'm going to give you a procedure. Well, this is a theorem due to Goodstein, proved in 1944. And I'm just going to illustrate it with a particular example, but it applies to any natural number whatsoever, what I want to say. I'm going to give you an example just to see how it works. I'm going to take 1077. Now what I do first is express this in binary form. So you've got 1, 0, 0, 0, 0. When I write it in purple or something, these are binary numbers. What does that mean? Well, each of these numbers represents a power of 2. So it means it's 1024 plus 32 plus 16 plus 4 plus 1. Any natural number is always a sum of distinct powers of 2, and that's what a binary expansion is about. So we have done that. That's nothing controversial or anything about that. But then you might say, well, I haven't done these, I haven't put these things in binary. I've used ordinary denary notation for that. So, but let's write those as sums of powers of 2 as well. So what's 10? Well, it's 2 cubed plus 2. That's 8 plus 2. 5 is 2 squared plus 1. 4 is 2 to the 2, and so on. So I've done that. Okay? And then you say, well, I haven't really finished, because look at that 3 up there. I should write that as 2 to the 2 plus 1. Okay. So that is 2, so 2, the 3 is 2 to the 1 plus 1. Okay. So you might have to invent towers which are bigger than that, because I might get some more numbers here which weren't written this way. But after a point, it'll come to an end, and the numbers will be expressed in this sort of a way. Now I want to define 2 procedures. The first procedure is to look at all the 2's here and replace them by 3's. Okay, that number has got enormously larger, but it's a perfectly well-defined procedure. That's procedure A. Procedure B is subtract 1. Okay, there's a handy little 1 hanging on the end there, so that's B. Going from the red ones to the green ones has made the number get enormously larger. Subtracting the 1 is just a tiddly little bit smaller. Okay, now I do this again. Now I've got lots of 3's. Procedure A is to replace all the 3's by 4's. Hugely larger again. Subtract 1. It's a little more difficult now because, of course, 4 to the 4, there isn't a handy 1 sitting at the end, but it's like subtracting 1 from 10,000 or something, 9,999. But with base 4, you've got 3's instead of 9's. Okay, well, you can do that. And then you replace all the 4's by 5's, subtract 1, and so on. It's a perfectly well-defined procedure. The numbers get larger and larger. We started with 1077, then they get bigger and bigger. That's about 10 to the 40. The purple one's about 10 to the 600. The bronze ones are about 10 to the 10,000. And they get bigger and bigger and bigger and bigger. And where do they get? 0. Every number you start with, no matter how big, you end up with 0. That's Goodstein's theorem, that you always get 0, whichever number you start off with. And it's a theorem more recently, due to Harris and Kirby, that you cannot prove Goodstein's theorem using these procedures. It is an example of a Gödel theorem, which is simple enough that you explain it to somebody who's not a mathematician. You just have to know what experiments mean. That's basically it. So this is a very remarkable result. I would not recommend you go home and using it on your home calculator. Why don't we try 4? It's actually 1077. 3 stops very, comes up and goes down, doesn't go very far up. 4. Now try that one. Try it with 4. I would not recommend using your home computer. I would not recommend using the university mainframe. I would not recommend using any computer. The number goes up absolutely enormously before it starts to come down again. And you might say, well, how on earth do you know that this must be true? Well, the actual way it's proved is using something called transfinite induction. But it's the sort of thing that you could sort of get a feeling for when you play with it for a bit. You see, what happens is you have these big towers of exponents, and there's a lot of stuff going on down here, and then it hits, when you keep subtracting one, and then it hits another one of these, and then it tumbles down, and it tumbles down, and eventually it hits the bigger ones, and you get a feeling, and you see why it's going to get smaller and smaller. It's a bit of a subtle reason that it always works, but it's not a very difficult piece of mathematics once you know the right things. So, okay, it's certainly true.
Roger, sorry, is it the limit of this equals 0? What's your claim?
Yes, the limit is you keep on doing this procedure, A, B, A, B, A, B, A, B, A, B, A, B, and you get 0.
Find it in many steps.
Yeah?
Yes.
Hard to believe. It's hard to believe, but you do get 0. Try it with 3, and that's not so hard to see why you get 0. And then try it with 4, and maybe you can convince yourself it will give you 0 eventually. That's good enough. But it's more subtle than that, clearly. Yeah? Even though these numbers look as though they're going up and up and up, it's a good Achilles and the tortoise example, you see. The tortoise wins, eventually. Subtracting 1 simply in the end wins. But in the end is an incredible length of time. Okay. In fact, that's quite important, the fact that it's an incredible length of time. So let me leave you with that thought. I'm not going to prove it here, but I'll leave you with that thought. Okay, so what this Gödel thing seems to be telling us, I mean, what's going on? How do we know that G of R is true? Well, you can follow through the argument. It's one of these arguments that sort of turns on its tail, and you can see it is a subtle argument, and it depends on sort of coding things in a certain way and then assigning numbers to the codes and so on like that. But the actual logic involved is not that difficult when you get it. But it's not worth my trying to explain here because I think it would make take too long. Let me try and raise, you see, you might say, what does this tell us from understanding in relation to computers? Well, it seems to me it's telling us that we do not use something like R to establish mathematical truth. How we know certain things are true in mathematics are by using understanding, and it can be used in subtle ways, and understanding whatever it is not something that you can encode in a computational procedure. Now that's what it tells me, and of course a lot of people don't like that, particularly if they're working in artificial intelligence, and so they try and find ways around it. So let me give you some of the arguments against it. The argument most commonly raised against what I call the Gödelian case is that, in case that we are non-computational beings, well, the errors argument is interesting because this was Turing's reason. Turing's a very interesting example here because it seems, I mean, in his early work before the war, the Second World War, he actually did try and explore things more general than computers. It didn't kind of get in very far. I mean, very interesting ideas. But the fact that he was trying to do that suggests that he was exploring the possibility that there might be things that you could talk about sensibly, mathematically, which went beyond what we understand by computing today. But then, during the war and later, he got so engrossed in the ideas of what computers can do that he seemed to have changed his viewpoint rather and taken the view that, well, the let-out to the argument I just gave you is more or less this one, it's kind of the errors argument, that human mathematicians make errors so that rigorous Gödel-type arguments do not apply. I personally think this is a very unlikely let-out, and let me just give you a quote from Turing, actually. This is a lecture he gave to the London Mathematical Society in 1947, and he said, if a machine is expected to be infallible, it cannot also be intelligent. There are several theorems, and this thing I was just telling you is what he meant, basically, which say almost exactly that. But these theorems say nothing about how much intelligence may be displayed if a machine makes no pretense at infallibility. So he thought it's really the fact that humans make mistakes that make them superior. Now I find that very implausible for various reasons. Well, we make errors. The errors can be corrected. Others can correct us, and you say, "Oh gosh, yes, that was a mistake." It's not as though it's this sort of inbuilt thing that you can't see. The errors that human beings make. Well, I would say people who are at least rational human beings are correctable, either by the mathematician or by some other person who's made a mistake. Oh my God, so I did that sort of thing. Also, it's easy to make computers make mistakes. So it seems to me that this isn't a very good argument. And I hate to say it's not good. I mean, because Turing, I have tremendous respect for him, but I do find this not a very plausible explanation. Particularly here, I mean, you can make computers make mistakes, and it doesn't make them superior. So, well, I don't know. Okay, what about the other ones? The extreme complication argument. That you might say that algorithms governing human mathematical understanding are so vastly complicated that their Gödel statements are completely beyond reach. Well, I also find that rather implausible. You might say, for example, Euclid's famous proof that there is no largest prime number. Nobody said, well, you see, he says you multiply together all the primes less than that number and then construct a prime, which is either bigger than it or you've left it out. It's quite a straightforward argument. Somebody might come along and say, well, some of those numbers might be so big that you would never be able to write them down in the observable universe. I mean, to a mathematician, that's not an argument. So it seems to me that the complication argument isn't. But I'll give you something else, which I find perhaps more convincing. The other one is ignorance. Now, this is the better argument. This is Gödel's own let-out. I should say that Gödel would be on my side in this argument, in a sense. He would be on my side because he was really taking this point of view as saying that we are not computers. However, he took the point of view that the mind was something beyond the brain, and that I'm not doing. I'm saying that the brain, whatever the mind is a feature or manifestation or something of what the brain is doing. And so I have a different way around, which I shall come to shortly. But I think this is actually not, it's not an argument that you do have to take seriously, that you don't necessarily know R, you see. And here, in order to construct G of R, you have to know what R is, and you have to believe it. So his view was maybe there was some fantastically complicated algorithm in our heads, and that was something we couldn't know. Now, there's a real trouble with that sort of argument, which has to do with, well, let me use this version here. This is a cartoon from my book, Shadows of the Mind, which I drew to illustrate various things. But the idea is, if there was some such complicated algorithm or something in our heads, how on earth could it have come about? You see, it's got to be able to handle the Goodstein theorem, for example. And the Goodstein theorem requires going to numbers which are so ridiculously enormous that our ancestors would certainly not have encountered them or even considered them. So how is it, and this is the more general argument here, it's trying to say that it's not much of or any selective advantage to be a mathematician. And I think that's probably true now, as true now as it ever was. But here you see I have this poor fellow who's evidently a mathematician, proving some quite subtle theorem actually. But he's so engrossed in what he's doing that he's not going to notice that he's going to be eaten by a saber-toothed tiger any minute. So, whereas his cousins all over here are doing more directly useful things with their understandings, like growing crops and domesticating animals and building houses and building mammoth traps and things like that, which evidently were useful to their evolution. Whereas to do sophisticated mathematics of the kind, say like the Goodstein theorem, has no advantage whatsoever, as far as I can see, with regard to the kind of development of consciousness, understanding, and so on. It's something quite different. Consciousness and understanding was something which evolved, which was of a selective advantage, I'm sure, but it was not so as to enable us to do sophisticated mathematics. That seems to me not the reason for it at all. So I really don't see how this, very sophisticated, unknowable algorithm could conceivably have come about by natural selection. That applies also to both these arguments here. Seem to me to be very hard to get round from the standard point of view of natural selection. So let me just leave you with that. That's more or less, I'm prepared to say that these arguments do seem to me to suggest that there is something fundamentally outside computation going on in our brains, and it has to do also, specifically to do with conscious understanding. Well, there is a question here of where do we draw the line. Some people say, oh, well, all you've done is shown that mathematical understanding, that's not terribly important or something, I don't know. Well, if that's non-computational, what does it say about the rest of, well, you see, I don't happen to think that there's anything very specific about mathematical understanding beyond understanding generally. It's just a feature of our ability to understand whatever it is. And I said I don't really know what understanding is, but whatever it is, it has tremendous power in our evolution. And it's not just for mathematics, that's just because I can prove something in mathematics. It's not because I think of it as being specific to mathematics at all, which I certainly do not. What about human consciousness? Well, I do think that that's an important aspect, but then you might draw the line somewhere else. Human consciousness, what about animal consciousness? I would hate to draw a line between these two. It seems to me that animals, many of them at least, are so much like us that to try and draw a big line, I'm not drawing a line between mathematicians and non-mathematicians, certainly, and I'm not drawing one between human understanding and human consciousness, and I'm certainly not drawing it here either. However, I would be prepared perhaps to think of drawing it between animal consciousness and life. So I would regard consciousness to be the key issue where we really do need something outside computation. So that's what I'm saying, beyond computation. Now, if you believe, as I do, that whatever is going on in our heads, and consciousness being something I would believe is going on in our heads, if you like, mainly, what kind of physics might be involved here? And then, however, what you could do here is something a little more sophisticated. It's called a Mach-Zehnder interferometer. Here we have a beam splitter again, ordinary mirrors here and here, and another beam splitter such that these lengths are all equal here. This is a square in there. And you might say, well, if it's like a particle, the particle might go this way, and if it goes this way, then it might go this way or this way. If it goes this way, it might go this way or this way. So it's going to be 50% chance of this and 50% chance of that. That's not what happens. What happens is that it's always this one that detects the photon. And to understand that, well, now you don't think of it as a particle, you think of it as a little wave, and the little wave gets split, and then the waves add up this way and they cancel out this way, and so you can understand it. If it's a little particle which has still got ripples and it's like a wave, okay, a wave packet would be an explanation for this one. But then it doesn't work for this. You go back to this one, you say, suppose it was a little wave, and when it hit this thing, there's a 50% chance of activating, and hit this, 50% chance. That would mean, okay, equally many times this is this, but half the time it would be either both of them registering a photon, or neither of them. So little waves don't explain this one. They explain that one, but they don't explain this one. So you're stuck. Unless you're Schrödinger or Heisenberg or something. And what they do is the following. Completely crazy, but it works. And what you do is you say, well, the photon does both things at once, and it does both things at once in a way which is weighted. You see, if there were probabilities of doing one thing or the other, then you'd have weighting factors here of these two alternatives. I should say A is that route and B is that route. And if you say that the thing could do this with certain probability, that probability, you'd have probabilities here and here. But they're not probabilities, they're not even real numbers, they're complex numbers. In other words, you can plot them in the complex plane, and I won't go into the details of that at all, except to say that what you actually do when you have a detector is not... Yes, let me explain first of all. I'm using two letters here, U and R. What is U? U is what sometimes people call this unitary evolution. It's really the Schrödinger equation. The Schrödinger equation is a deterministic evolution. It tells you that what will happen to the state of the photon. So the state of the photon is this thing with two things happening at once, and it has certain properties which I'll tell you in a minute, the most important being linearity, which I'll say. So it has certain properties of evolution. It's deterministic evolution of the state. However, when you make a measurement, and that's what these detectors are doing, you do something completely different. You then look at these numbers sitting here, you see where they're on the complex plane, you take the distance from the origin, square each of them, that's the squared modulus, and then those things are the ratios of the probabilities of each outcome. It's a completely different thing, and in a certain sense inconsistent with each other. So that's why I'm calling R, that's the reduction of the state, U is the Schrödinger equation. I want to tell you some very specific property that the Schrödinger equation has, which is called linearity. So that means that according to U, or the Schrödinger equation, alternative A, whatever it does at some evolution, whatever B it does at some other evolution, and the total evolution just continues with each of them evolving in its own merry way without paying any attention to the other one. I don't know how happy to be about that, but never mind. I'm going to give you my version of Schrödinger's cat. Here we got a photon going along, coming from this laser, hitting a detector, and it triggers a gun which kills a poor cat. Well, you might say that's pretty cruel. Well, of course, it's only a thought experiment, so there's nothing cruel about it. It's clearly only a thought experiment. But let's, nevertheless, even though it's a thought experiment, let's be a bit kind to the cat, and we'll reflect it off a mirror, and the cat's fine. But of course, you know what I'm going to do. I'm going to replace that by a beam splitter, and then, as Schrödinger tells us, the state is a superposition of a live and dead cat. Now, Schrödinger did not put this forward as an interesting experiment that you might try and do in the lab. No, he was saying, don't do that experiment, because he was a very humane person, and he would certainly not have been, he wasn't even an experimentalist, but he wouldn't have suggested such a thing to anybody seriously. He was saying, this is a pretty good demonstration that my equation, that Schrödinger's equation, is not the whole story. You don't see superpositions of live and dead cats. There's something else going on. Now, if you try and I've often shown this to people who are, physicists, they say, well, you've forgotten to put in the environment. Okay. You have to realize that the environment is all entangled with the cat state. So here we are. I'll put the environment. Okay, there we are. And let's look at the other one. Okay, there's our cat. And there's its environment, a bit different, but nevertheless, it's still there. And here we go. Okay, what does that do? Nothing. I mean, okay, it might be harder to solve the equation than it was before, but you're still not any happier off. You've got a cat which is superposed life and death. I mean, well, it doesn't help too much. Oh, they say, no, you put to mean that the observer either is in one world or another world or something like that. I've never regarded that as a very clear explanation. My own view is this is all very well. It's just telling us that quantum mechanics is incomplete. As Einstein said, as Schrödinger evidently thought, and as Dirac said. So, if quantum mechanics is incomplete, in what way might it be incomplete? Well, as I have sort of been working in Einstein's general relativity for a long time, I think in terms of this sort of thing. I also have removed the cat from the experiment because it seems to me that it's introducing an unnecessary complication, because the cat no doubt has its own consciousness, as I would maintain, and if it has, then you have to know how to treat that, and so on, so you get stuck. But so let's not do it with a cat, let's do it with a lump of material. If the photon goes this way, it moves it from here to here. If it goes the other way, it stays put. And so you have a superposition of this lump of material in two different locations, and I'm supposing that in either one it would have been stationary, it would have just sat there. The question is this superposition stationary? Now, according to linear quantum mechanics as we understand it, Schrödinger equation quantum mechanics, unitary evolution quantum mechanics, that would also be a stationary state. However, if we consider the space-time, and here I have a diagram of the space-time with a little bit of a bump here, it's much exaggerated due to the presence of this lump here, and one of them gets moved and the other stays put, and you have now two space-times which are superimposed. Now, I don't want to go into the reasons behind believing this. I should say that Hungarian Yoshi had ideas very similar to these quite a bit before I did. I had ideas which were based on general relativistic principles, one of which I'll mention in a minute. But here is the formula that we both come up with, which is that there is a time scale for this superposition, that it will only last for a time that you can calculate. And it goes spontaneously into one or the other. It's a bit like a radioactive nucleus, which will decay in some time, or it won't decay in a certain time. And you, quantum mechanically says in the superposition of those two, that there is a time scale for that superposition. And that depends, by the Heisenberg time-energy uncertainty principle, on some uncertainty in the energy of the superposition. And if you try to work out what the energy of the superposition is, taking into consideration Einstein's general relativity, you come up with a formula like this, that this EG, which I'm calling it, is a nice way to understand it, that if these two states are simply a translation from one location to another, so I imagine it originally here, and I move it to here, and I imagine, say, there were two instances of that object in superposition originally. I pull one away from the other. I ask myself how much energy that cost me pulling against gravity, just gravity. And that is EG. So you can explain what EG is. I've got it at the bottom here. And that is EG, and this is the time scale. This is Planck's constant divided by 2 pi. And so that is the formula, which is a suggestion that this state, for good principles coming from Einstein's theory, that is a reasonable estimate for the lifetime. I'll come to experiments in a minute. It sort of involves gravity and quantum mechanics at the same time. People usually say, in physics, they say, well, that's ridiculous. Quantum gravity is a subject where you have to consider things like the so-called Planck length, which is 20 orders of magnitude smaller than ordinary particles. The Planck time, which is 10 to the minus 43 seconds, 20 orders of magnitude smaller than the fastest physical processes we know about. So these are ridiculously tiny things we never really know anything about, I guess, fair to say. But they all arise by multiplying two fundamental quantities. This G is Newton's gravitational constant, and this is Planck's constant over 2 pi. And so you're multiplying a very small quantity by another very small quantity, so you get a ridiculously small quantity. However, the formula I've just given you, I'm dividing a small quantity, that's this H thing, by something here which depends on the gravitational constant. So it really matters, you have to look at the details to see whether it is a long time or not. So it's an interesting question. And let me just quickly give you one of the arguments. I perhaps shouldn't say too much about this. This is just the argument which I'm giving you here, drawn again. This is the lump in one location, and I move it to 2, and these are representing 2 space-times. And you can find a measure of the distance, deviation between these 2 space-times, which depends on the time scale and on spatial considerations. And you measure that in these Planck units that I've just been talking about, these units here. And if that becomes a order unity, then that's the time that the thing does decay. So it tells you, there you are, done. You see what that region is, where both things are happening at once, and then after they're there, and then after a while only one of them persists. And that measure of that thing is of order unity in Planck units. That's a simple way of thinking about it. One of the fundamental principles you can use is Einstein's, or Galileo's I should say, principle of equivalence, which says that a gravitational field is equivalent to an acceleration, and that if you Galileo here imagined to be dropping a big rock and a little rock from the top of the Leaning Tower, and then here's an insect sitting on one rock looking at the other, and that's to that insect the gravitational field of the Earth has been cancelled out. And is that consistent with quantum mechanics? That's the question. And you look at that, and due to some subtleties which I won't try to explain to you, you come up again with this formula, the H cross over EG formula. So maybe that is a true formula. Is it true? You don't know. I have colleagues. Dirk Baumeister is the main colleague. He was a former student of mine. There's a lot of other people working on this now. This is quite an old slide. But he's still working on this. He's been doing it for about 10 years. Last time I saw him, which was about 1.5 years ago, quite uncharacteristically, he said, give me 10 years and I'll have an answer. Well, that was less than 8.5 years now. So I'm counting him down. Basically, the idea of experiment is you have similar to things I've just been showing you. You have a photon, a laser, hitting a photon. The photon goes two ways, splitting these two routes. This one you keep it in a cavity, bouncing backwards and forwards. Here you keep it in another cavity, bouncing backwards and forwards. Here is a nice hemispherical mirror, actually. And it fits this little tiny mirror, which I've imagined larger here. It's about a 10 micron cube. It's about a tenth of the thickness of a human hair. And if the photon keeps hitting it, it will just move it in an order of seconds to minutes by about enough to displace the nuclei. Here, this is a picture of the nuclei displaced by a nuclear diameter. And that's when the effect, if it's true, would be at its maximum. So you could work out what the EG is, and you would come out with an answer that it would be a matter of seconds to minutes, depending on the details of the experiment. If you can keep it for longer than that, that would show I'm wrong. If it spontaneously goes one or the other in that time scale, well, either there's something wrong with the experiment, or maybe it's right. So that's the idea. Okay, that's the basic scheme. This is Dioshi, I should say, had very much, I don't think he had this experiment, but he does have the same scheme. Okay, what's the relevance of the brain? Well, you see, I tried to, when I wrote my book, The Emperor's New Mind, I didn't really know enough. And I hoped that by the time I get to the end of the book, I would have a clue as to what the answer is. I didn't. However, it was an advantage because Stuart Hamroff read my book and he proposed something which I had never, in my ignorance, had never heard of. See, this is really thinking about ordinary synaptic neurons and so on. It didn't seem to me you're going to be able to preserve quantum coherence in a neuron. You have magnetic electric fields which go outside as you disturb the environment in ways which are completely uncontrollable. So it seemed to me this was not going to work. However, it didn't stop me writing the book. Maybe it should have. But then Stuart Hamroff came up and suggested that microtubules might be playing a key role. And I said, microtubules, what's this? I should say, I get lots of letters from people which are completely crazy. And so here was another one. This book did have actually pictures of microtubules, and I said, well, that's a bit serious. So I went and looked it up and said, yeah, there are such things. And so on.
Solution, yes, solution of Schrödinger paradox might due to decoherence, because due to decoherence we know that no human observer can see these interferences because they exist for a very small time.
Well, of course, that would...
The second question...
Okay. Do you want me to answer that one
about
first?
decoherence.
Yes.
What's your answer to Tegmark's remarks that if you look on your microtubules, the decoherence is so strong that you cannot see quantum effects?
Yeah, I mean, that's the same question, I think. No, I just think that, you see, Tegmark's arguments were based on a very simple picture. In fact, they were not the right picture. That's perhaps not too important. The important thing is, yes, it's very remarkable if you could preserve coherence in such structures. Now, the thing is, one important point to bear in mind here is that you only have to preserve coherence in certain degrees of freedom. And these degrees of freedom have to be well shielded from the outside. Now ordered water and all sorts of things are possible ways in which you might shield this kind of coherence from the outside world. It's obviously the key thing, and I agree with you completely. You have to see how you could possibly prevent these things from decohering, and that's right. And most physicists would say, well, clearly it's due with neurons. Obviously, and I would agree completely there, because you know that with neurons, the nerve signals do have electric fields which invade neighboring other cells and so on. So there's no question that there is a fundamental problem for conserving coherence. Whereas with the microtubules, what's actually going on there is much more subtle. And you might ask the same question in connection with Bandyopadhyay's results, because he does seem to see something of a quantum mechanical character which persists at high temperatures. And so we have to understand what's going on there. I'm not disagreeing with your question because I think it is the right question. And certainly a scheme like this, you have to have an understanding of how you can preserve at least some degrees of freedom which are key to this whole process in a way which does not decohere. It's the sort of thing that does seem to be going on in Bandyopadhyay's experiments, that you seem to see that there is some kind of shielding of at least some degrees of freedom from decoherence. Well, how that's coming about in detail would have to be understood. But you can see a lot of these arguments apply to things like high-temperature superconductors. So high-temperature superconductors, low-temperature ones, which are near absolute zero, well then you can understand, you can preserve coherence down there. But these high-temperature ones, okay, they're not body temperature, but they're about halfway to body temperature, which is already a bit of a mystery why they do not decohere. And as far as I'm aware, there is no good physical explanation for why high-temperature superconductivity works. So we see that problem. Doesn't mean that we have an answer to that problem there, but it's a similar problem of a similar ilk, where you do seem to find large-scale quantum activities taking place coherently, where you might at first sight, or first thought, or first whatever it is, have believed that they should have decohered. But it's certainly the right question to ask. Yes.
So if this experiment is correct, Bandyopadhyay,
Yes.
it is the same as the discovery of the temperature.
Superconductivity for hydrogen?
I think it's
It's
important.
the same thing? Yes.
It's not exactly.
Nobel Prize.
Yeah, it's not exactly high temperature. I mean, he doesn't claim it's superconductivity. Ballistic conductance, well, maybe with a very long microtubule, it might compete with superconductivity. It's not that good, but it's much better than you would have expected in a biological system. As far as I'm aware, it's by far the most conductive system that's been found in biology.
In the first part of your talk, you showed that kind of usual mathematics with your example of Goldstein's theorem, right? It's not computable. So we are doing in kind of standard mathematics something which we cannot formalize with this computable procedure, right? Then I assume that kind of mathematics we use in physics, and I now even mean very classical physics, something like differential equation and stuff. So I assume by the same argument it is not computable either, generally, right? So physicists not usually use formalized version of something, but just use, say, in problem. And then I don't quite understand this idea that, say, classical physics must be computable because it's somehow based on mathematics, which is, I assume, is not.
Well, I mean, you're raising. Sorry. Have you finished? No.
Yeah, I finished.
No, I tried to touch on this point, but only rather briefly. And perhaps this is what you're addressing. Because when you're talking about continuous systems, you have to know what computable means. And one of the great advantages about discrete systems is we have one notion of computability, and that notion, there were many, many different proposals that people came up with, Turing, Gödel, and Post, all sorts of people came up with, and Curry, and so on. Church, yes. And these different procedures all turned out to be equivalent. And so it seems that there was one overriding fundamental notion of computability that pretty well everyone agreed about. But when you talk about continuous systems, there seems to be no consensus whatsoever. There are many different points of view. Now, I think perhaps I did gloss over it rather too quickly, and I think it's something well worth studying more. To what extent does the Turing argument, if you like, and here I'm using the Turing argument where he tried to say that using continuous parameters is not really that important. That you could use approximations and these approximations are good enough. I don't really quite agree with that, because when you have chaotic systems, when you have systems of various kinds where you're not quite sure how the error is going to come in and so on. That there are subtleties here, and I think perhaps this is the sort of thing you're saying, which I do agree with. I think all I'm saying for the purposes of this talk, that for the purpose of this talk, I'm trying to say, well, let's assume that that's not where the issue lies. It may be that there are subtleties about using continuous parameters which give you something quite different in physical systems that you might be able to construct. See, the usual problem is that the issues come about when you're looking at very tiny, how precisely can you define your system? And there are errors in that. And so we have to say, well, does it matter whether we're a little bit out or not? And then if it's a chaotic system, then of course an exponential dependence on how far out it is. And these things might cause a problem. But nevertheless, computable or not, and you might say, you've got a system which is very sensitive to very small changes in the data. But nevertheless, if you put in the same data, you always get the same answer. Now, is that a big issue here? And if you're saying that yes, we need to think about that more, I'm agreeing with you, because I think that there is an issue there which possibly is a let-out to the argument. But my argument is to say, well, I'm going to assume that that's not the case, and the let-out is somewhere else, because it's usually not. It's things where you're really different in how precisely you put the initial state in. It's not quite the sort of thing that's kind of relevant to. Well, let me not go into that further. I don't tend to think that's where the problem lies. But that doesn't mean I don't think you should think about it. I think it's very important. And I think it would be very nice to have proper mathematical theorems of that nature, which, depending on what viewpoint you take, with what you mean by continuous computability and so on, and to what extent do you get genuine non-computable effects on it. I mean, the things that Paul and Richards worked on, one particular interpretation, and they said if you have a certain degree of differentiability, it wasn't big enough, then you would get non-computable behavior. Now, is that seriously that you think about here or not? Good question, but I don't know the answer. But my own opinion is that it's unlikely to be the real answer.
Some other questions?
Yes? Is the question written down?
Yes.
Okay, hold on. Should I read this out?
Well, that's up to you.
Well, I read the question. Oh, there's several questions. Well, I read only one very sentence. Is it possible that there is really totally independent, sorry, there is a reality totally independent of the mind that conceives it? I would continue. It is impossible that there is a mind totally independent of reality which is it tries to conceive. And what we really have is reality-mediated minds that are trying to conceive mind-mediated reality. It depends on the time to try and understand that. So I think I've done a lot address it at the moment. I think Poincaré is probably expressing a view which is different from mine there. Questions are, what if our difficulties, including the known paradoxes, are offsprings of the fact that modern science still operates within the frame of reality-free minds? Conceiving... I'm having trouble with these questions, I think. I'm not sure
Well, it's okay.
Perhaps... I think it's easier if there's somebody asking a question and I can ask.
Yes, you might come up.
Yes.
So, I'm a theoretical computer scientist, so it's
Yes,
very interesting talking. I'm just wondering, it's a little different question. So, I understood that you would like to model or understand consciousness by using quantum mechanics or maybe quantum computation.
No,
So,
I'm trying to say it's beyond that.
okay.
I'm trying to say, as we understand quantum computation, it's only a speed up.
Mm-hmm.
It's not enabling you to prove.
So that might be the answer to my
Yes,
question.
okay.
So how about us trying to use the
Yes.
computational model other than DNA computing? And that explains how nature computes, how the computational processes are done in nature. So do you think that would make any sense to me?
But I think if you say how nature computes, that's already begging questions.
Yeah, that's his model is trying to explain that.
Yes. I should perhaps mention one important point in relation to quantum computing, and that is, I didn't address this, but it's certainly, if you want to evolve the Schrödinger equation, you have an exponential depends exponentially on the number of degrees of freedom. It's quite unlike classical. So if you try to simulate a quantum system classically, it's extremely inefficient. And so one of the big uses of quantum computers might well be to simulate quantum systems, because that's already using the quantum procedures to simulate quantum processes. That could be a powerful.
And that's also true for DNA computing.
Yes, I can understand that. It's possible. Yeah. Yes. No, I'm nothing against that. It's just that I don't think it answers my question, because I'm not talking about the difficulty or the length of time it takes to compute things. I'm talking about computability, which transcends all those things. I mean, there could be of relevance to these issues in specific cases, but it doesn't directly address the question I'm talking about.
More questions? So I have a question. If the next asteroid will be more active and arrives in time at the needed place and kills all the human beings, where mathematics will be since then?
Our mathematics is the problem. But maybe people will see it coming and they will hurriedly send messages of various theorems they proved out, hoping that some distant intelligence will pick these things up. But there is a slightly different answer, which is the talk I'm giving in Moscow, which is relevant to this. But it's rather more science fiction, I have to say, than what I've been saying today. But there are issues there, yes.
Thank you. Any more questions? Yes. Will you come up?
Well, actually, the question is about the model of non-computable physics you talked about. So you talk about time, right? And silence.
Yes?
You have a set of polynomials and
Volume.
Polynomials, yes?
and you look, yeah. And you look at whether you can actually.
Can you move the microphone closer to your mouth? That's what I missed.
Okay.
Yes.
Okay. So, and you look at if you can actually tile the plane with this set of polynomials, and you say that this dynamical system is non-computable.
Yes.
Well, the question is, what exactly the non-computability is? Let me state my question. It may be a stupid question, but it is a question still. Whether given a set of polynomials,
Yes.
is it true that you can check that you can tile the whole plane, or there is some set of polynomials for which it is not provable?
Let me put it like this. The real statement is that you can prove that it will not tile the plane. If you have any set of polynomials, there is an algorithm which will establish, if it is the case that they will not tile the plane, there is an algorithm for establishing that fact. But the problem is the other way around. If it will tile the plane, how do you know it does? You see, if you could give a period parallelogram and you say, well, look, this works as a period parallelogram, okay, that's fine. But that's the problem. That these other sets of tilings, like the one I showed, they don't have any period parallelogram. Now, you might be able to prove by some means that they tile a plane. Indeed, you can. I can prove it for you, that it does tile a plane. But then, whatever system of rules I have, there will be others which transcend those rules. Because you could construct a set of tiles out of the rules, which those rules could not deal with. So it's like that. So you will always find, no matter what the rules are, if they are computational rules, there will be a set of polynomials that will tile the plane.
The question is about computability, and if you know, there's Marcus Hutter,